How you doing?
Hey Louis.
How are you?
I'm good. How are you?
Good. Hello, class. So, in this demo, I like to demonstrate a little bit Faraday's law. And one of the most important applications of Faraday's law is the inductor. This is a circuit element. It's a wire coiled up. And if you had a steady current, it would be nothing special. You just have a steady current through a wire. But interesting thing happens if the current is changing. This is an inductor here.
So because of the coil, we will have magnetic field inside the coil. And the change of current will induce an EMF. So here we have iron core inside the coil. This is pretty heavy. And it will help to increase the magnetic field.
Yeah, so this is exactly Faraday's law. So I have these wires. They're making a coil. As the current goes through, I get a magnetic field. All good. But then the idea, as you just said, if the current is changing, then the magnetic flux inside will change. And if I have a changing magnetic flux, I will have an induced EMF.
Right.
Essentially, the wire, the inductor is fighting the change in magnetic field. If you're trying to start the current, it will say, whoa, you're trying to create a magnetic field. It will oppose that. And while it does that, it creates an opposing voltage to what you're putting in. So it's trying to oppose the change. And on the other hand, if you stop the current, it doesn't want it to stop, and so it will keep going. So essentially, an inductor kind of tries to slow down any changes that happen in a circuit.
It's like the inductor has a momentum, but inertia.
Yeah, it's like it has some inertia, exactly. It doesn't want to change so quickly in a circuit diagram. So this is a nice little setup here where I have a resistor and just connect directly to the power source, voltage source, just a resistor. And then this one, I have the inductor, this massive inductor, in line with this light bulb. So if I turn it on, this inductor is not going to like it right away to create a new magnetic field. It's going to want to oppose that. So we should have some kind of delay. Let's see what we have. Not too long, but indeed, this one lights up right away. And this one takes like 1 extra second to light. What happens if you take the core away?
Let's do it.
Oh, it looks heavy. So let's see now. Almost no delay. So this core really was really important to increase the inductance of this guy. And without it, it's still an inductor, but almost not noticeable. It's very hard to get an effect from an inductor in a circuit.
Let's put this back.
Yeah. And the opposite is true too. If you have a current flowing and you suddenly stop it from flowing, for example, you open the circuit, the inductor is going to say, whoa, I don't want this current to stop. I don't want this magnetic field I want this magnetic field to stay where it is, so I need to keep up the current, and there will be an induced EMF there too. Right?
Right.
What is this?
So let's look at this system here. So I have a 9-volt battery, a neon light bulb, and a really big inductor, and they're all connected in parallel. So the neon light bulb will require at least 100 volts of voltage potential in order for it to be turned on. So here, if I just close the circuit, so right now just the battery and the neon light bulb and nothing happens. But if I connect the inductor to the circuit and I just suddenly switch off the circuit, you can see the light bulb just light on momentarily.
So wait a minute, did you say how many volts do you need for this?
100 volts.
100 volts.
Yes.
Okay, let me get this straight. So you're saying we have a 9-volt battery, and that's not enough. It's like not 100, it's 9. And then I just put this inductor, nothing's changing. But then you open the circuit, and you get 100 volts. Wow.
Yes.
I see. So this is a good example of essentially there's a field here. There's a magnetic field inside the inductor, and when I open the circuit, there's a sudden collapse. We completely stop the current. Mm-hmm. There's going to be a very quick change in the magnetic field, and if it's really, really quick, I can get a huge EMF. So I can get all the way to 100 volt, and indeed, then I can light this up. Do you know this is, I think, how spark plugs worked in whole car or used to work? Now I think they use transistors. But back in the days, it was just a big inductor. In fact, this is one of them. It's called a choke. And then you have a choke that's charged with the 12-volt battery of the car, and you just open the circuit, and you can get really high voltage, you can get sparks, and you can turn on your car even in winter. Pretty neat.
Pretty neat.
That's inductors for you.